In this session, we are going to discuss proximity measure for symmetric versus asymmetric binary variables. For binary variables, we usually represent their occurrences using contingency table. Okay. Suppose we have two objects, I and j. The number of times they both appear could be q, they both missing could be t cases. I appears and j does not, there are r cases, and I does not appear and j appears s times. Then for symmetric binary variables, that means the chance they appear or they not appear actually have equivalent chances or approximately the same chances. We call these as symmetric binary variables. In that case, their distance, like r and s, these two cases, they are different. So their distance measure is r plus s divided by all the cases. Okay. For asymmetric binary, usually we assume they both appear, the case is much rarer than they both not appearing. Okay. So for these asymmetric variables, they are different. It's r plus s, but they both not appearing. That case actually is t is not so important. The reason is, for example, in medical test, only the positive one will attract attention. Okay. Then for that distance measure, we look at r plus s divided by q plus r plus s. That means all the cases with t cases removed. Okay. Then for their similarity measure, that means how many times they are the same, actually it's the q cases. For the q cases, we probably can see that's the same denominator. Okay. Actually, Jacob coefficient was somehow rediscovered in the pattern discovery field. They call this one coherence. Actually, this coherence definition, if you really map them into this contingency table, they have the same definition as Jacob coefficient. So then we look at the rare cases. Suppose we have some medical tests. Then we have Jack, Mary, and Jim, three cases, three people. Their test actually is represented in this table. We can map them into a contingency table. Okay. So since gender, the chance to be male and female are roughly equivalent, so this is symmetric cases. So for us, we are only interested in asymmetric cases. That means the remaining attributes becomes more important. Then we try to examine how they are different. Suppose we say 1p is positive case and a value n, no or not the case, will be 0. Okay. In that case, we look at our distance measure for asymmetric attributes. We can work out these contingency table. For example, for Jack and Mary, we probably see Jack and Mary, they are the same positive case, like both have fever, both the test 1 actually is positive. There are two such cases. Okay. They are both negative, like a cough, test 2 and test 4. Actually, there are three cases, they are both negative, but they do have one case, they are different. Okay. So similarly, we can work a contingency table for Jack and Jim, Jim and Mary. Okay. In this case, we can calculate their difference. Probably we can easily see Jack and Mary actually are most similar. Jim and Mary are most different. We may conclude that Jack and Mary may have similar disease in this case. Okay.